In this video, I'll demonstrate how to emulate wide area network latency, jitter, and packet loss for free in your Homelab using simple Linux commands on a virtual machine. After the demo, I'll explain the commands that are being used and give you an idea of how realistic this method is. My name's Tad, and in my day job as a performance engineer, I often find myself wanting to be able to test application performance over various kinds of troublesome network links, such as high latency or high packet loss. Back in my software engineering days, we heard about a mythical creature called a genre box that our network engineers could insert in a physical network path that would emulate all kinds of WAN illnesses. The idea was that developers could see how their application would perform when they deployed across a slow wide area network long ahead of time before they ever actually needed to do so. And this is great, but unfortunately, I've never actually seen one in the wild. And it's just this kind of specialty device that's often expensive and not very accessible when you need it. Besides, with things like AWS, these days you most likely won't have physical access to a network cable that's connected to your server. I was recently investigating the effects of WAN latency on the Microsoft SMB protocol used by NAS shares, and I started looking into ways to emulate that latency without having to find a coworker in India or in the UK who'd be willing to have a working session. Enter the Linux TC command. It's a neat command that does a pretty darn good job of emulating network bottlenecks. It's easy to use and the price is right. Let's get to it. For the demo, on the left, I have a Linux virtual machine running in VirtualBox. And on the right, I have a terminal window on my Mac. So we start out by pinging the virtual machine, ping bozo.local, and you see the sub-millisecond response times there. And then we're going to copy a 170 megabyte disk image, and it's going to be instantaneous. Check that out. And that's what you expect. Now let's delete it. Now we'll go to the Linux box and we will insert some fake latency. So we use sudo tc qdisk add dev, and then we put the device name. And we put it at the root level, and we use netem, and we say delay of 70 milliseconds. That is New York to London. Now we ping, and check it out. Now we have 70 milliseconds of delay. 72, 74. It really does look like we are going from New York to London. Let's do the same file copy, 170 megabyte file. I'm going to open up the progress bar here so we can see how it's preparing. What is it doing now? It's taking its own sweet time is what it's doing. 21 megs. And you can see the pings are still going on in the background. Now we got 41 megs. So we'll let this go. And at the end, we'll see just how fast the performance was. You see now we're going about 2.6 megabytes per second. And we gave it a fighting chance. Everything was warmed up. We had already copied this over before. And even so, it's still taking way longer with this latency. I'll delete the file pretty fast. Now let's go back and turn this delay off. Sudo tc qdisk del for delete dev, put the device name at the root level. Suddenly we'll see our pings, our sub-millisecond again, and we'll copy the file over and it should go instantaneously. As a bonus, we'll copy over an Ubuntu image, 2.13 gigs, and we'll see how fast that's moving over. There you have it. That's how you can add some false latency into a network stream. So this is how it works. In the Linux operating system, we have this idea of a mechanism to manage the traffic that's going between your IP stack and the NIC card. And what they do is they could actually say, okay, the NIC card says whenever I'm ready to send packets, send a signal to the OS, and the OS will give me more data. The problem is then you've got the NIC saying, I'm ready, and the OS saying, okay, here's more data. And the NIC saying, I'm ready, and the OS saying, here's more data. And that introduces a delay that's unnecessary. And so the way Linux does this is they have this idea of a queue, a driver queue that's between the IP stack and the NIC. The NIC can always pull things out of that queue. So it's a queue that holds frames of data that are just ready to go, packets ready to be blasted out on the wire. If the NIC sees data, it can send it. And so the way that Linux feeds that particular queue is it uses a thing called a queuing discipline. This goes between the IP stack and the NIC. And the queuing discipline is, there's many of them. This will, you can have like a round robin, you can have other kinds. What is going to help us is a queuing discipline referred to as NetEm, N-E-T-E-M. That is network emulation. That is a queuing discipline that will insert delays or drop packets and do various things that we want to do to emulate WAN network connection issues or WAN performance problems. And we use a thing called TC. That's traffic control to manage these queuing disciplines. This only applies to the outbound traffic, the traffic that is leaving the NIC. It doesn't apply to stuff coming in. So we use TC and we use this NetEm queuing discipline to insert 70 milliseconds of delay. So here's a standard TCP connection. You have your SYN going to the server, the SYN ACK coming back, and the ACK going to the server. And we're working on the client side. The way you do the latency in networking, when you look at the three-way handshake, is you simply draw a line anywhere you want because you capture in one place on this three-way handshake. Add up the differences between the packet at this point, and this point, this point, and this point. This is time going down. And it will work every time with this delay only being on the outbound packets. It's not a big issue. We're not delaying this ACK that comes back, but watch what happens. You insert a 70 millisecond delay. So let's just say we're capturing right here. Packet comes to you, that's time 0. Reflected from the server, there's your ACK, 0 milliseconds, it's right away. 5 milliseconds, plus 70, plus 5, and then you see the ACK come back. Total of 80 milliseconds of latency right here. What about if we capture over here on the client? The moment we capture the packet, that's 0, 70 plus 5, 75 milliseconds. Then we don't see our ACK back until 5 milliseconds later, so that's 80 milliseconds. And then we instantaneously see our ACK. Again, 80 milliseconds of latency. Let's look at this on the server side. And we'll see the same thing. Notice, though, how we only have the latency being applied in one place. Our SYN packet has no latency added to it. Our ACK packet has no latency added to it. But let's look at a three-way handshake. Say we capture on the client. We see that we spent 5 milliseconds going over, 70 milliseconds added of emulated latency plus another 5. Then we see 0. 70, 5, 80 milliseconds. And then what if we capture right on the server? That's our 0, 0, that's instantaneous. Then from here to here is 70 plus 5 plus 5, 80. So we get 80 milliseconds regardless of how we do it. This diagram illustrates the demo we just did. I put the Macintosh on the left side and the virtual Linux on the right side. You see our three-way handshake, SYN, SYN-ACK, ACK, and then we see closure of the TCP connection, FIN-ACK, FIN-ACK, and ACK. And I've put a little dot at each place where the latency is injected. And you'll notice that because of the way that the latency works, it's not injected on the packets that are coming into the NIC on the server. It's only injected on the packets that are leaving. It doesn't matter though, it still behaves in the same way, and we still get a full emulated 70 milliseconds as we saw in the demo. How realistic is it? In this blog article, Cody Brinkman from Oracle used Linux traffic control to help him simulate latency for testing fetch sizes in Oracle. And he was asking the very same question. At the very end, he compared real-time, real latency with the fake latency created by TC. And he produced these two graphs, the one on the left and the right, that show that the latency is virtually identical. And his conclusion was that TC is a very effective way of producing latency for testing performance. So that's all I have for you today. Thank you for watching.